Hello everyone, this is chapter 17 of the Crystal Clear Electronics video series called PWM with Microcontroller, written by Endre Szesztai. Please meet today's lead speaker, Szabolcs Veréb, assistant lecturer at the Budapest University of Technology. He specializes in power electronics, which is closely related to PWM, but more on that later.
Hello! Next to me is Dániel Piffkó, a fourth-year electrical engineering student, also at the Budapest University of Technology. His thesis deals with the application and testing of microcontrollers, so the subject of this chapter is not new for him. Before we begin, I'd like to add a personal tip to the curriculum. I encourage everyone to be curious in addition to practice. What I mean by that is to try new things. The curriculum gives you tools, and your electronic skills develop through practicing, so eventually you will be able to accomplish things that are not even in this curriculum. Anyway, look Danny, I have brought something with me. What do you think it is?
Goodness me. Well, I can see diodes, coils, capacitors, and even a larger transformer and a heatsink. So if I had to guess, I'd say it's a power supply.
You hit the nail on the head. It's a power supply. When I was in secondary school and got my driving license, an old family friend gave me my first car, a Renault 4. It was already 20 years old. It didn't have a music player, but I was really into music. In high school, I built all sorts of electronics in my workshop, typically some kind of audio amplifier for guitars and some simple music devices, so I decided to make something for my car. This power supply you can see here is the power supply for the subwoofer. Unfortunately, the 12-volt battery voltage wasn't enough to get the required power, so I used this power supply to convert the 12-volt into plus-minus 30-volt.
I can guess how, but can you tell the viewers how this relates to our topic today?
Certainly. This power supply operates in switching mode, which means it has MOSFET switches controlled by a PWM from an analog power supply IC. The IC is located somewhere on this small PCB. It was my first encounter with PWM in electronics, and since then, I have been working with similar power supplies. I also teach the operation and control of various power supplies at the university.
Are you going to give us a university lecture now?
No, you could do that, but I suggest we start from the basics and see how to make a PWM signal with a microcontroller. Then we'll continue at the university. In the previous chapters, we have learned about the essence of PWM. We switched between two voltage values with the overall period staying constant. If we increase the proportion of the on time to the period, the LED lit up brighter and the motor rotated faster. In practice, by varying the ratio of the two durations, we managed to influence the average voltage. This ratio is called the duty cycle. The initials PWM itself stand for pulse width modulation. The name refers to the fact that the average voltage value of a square waveform is proportional to the duty cycle, which is proportional to the duration of the on time. And modulation means that if you change the width of the pulse, which is the on time, the average voltage changes. This feature is important in two cases. First, if we would like to create an analog signal in a purely digital system, for example with a microcontroller, and also if we would like to control high-power signals, such as in motor control or power supplies. In light of the above, it isn't surprising that most microcontrollers include a PWM peripheral. It's a hardware unit within the microcontroller based on a digital counter timer circuit specifically designed to generate PWM signals. If we simplify it a little bit, all we need to do is to set the frequency and the duty cycle, and the PWM signal magically appears on one pin of the microcontroller. This pin can even drive an LED or a switching element such as a MOSFET directly. It's important to note that after these values are set, the generation of these PWM signals happens independently from the CPU, so it doesn't take valuable processor time away from other tasks. But we will talk about this later.
And why do we want to force the microcontroller to generate the PWM signal? Why not apply the already known 555 timer IC?
It's a great idea. You don't necessarily need a microcontroller to control the power supply. Instead, you can use an IC that is similar to the 555 timer IC, as I did in my power supply. However, using a microcontroller offers several advantages. For instance, you can easily change the power supply's functionality with a software update. On the other hand, if you're using an analog control IC, you would need to replace the components with a soldering iron to make any changes. Additionally, using a microcontroller allows you to incorporate modern functions like a Wi-Fi controlled RGB lamp.
Let's take a look at what a PWM controller, also known as a peripheral, can do.
A PWM controller can usually perform the following functions. It must always permit the setting of the PWM frequency, that is, the PWM period and the duty cycle. It's usually possible to generate an interrupt at the end of each period. We will discuss interrupts in more detail in another video later. You can generate interrupts not only at the end of the PWM period, but also at various internal events in the periphery. For example, when the logic state of the output PWM signal changes, that is, at rising or falling edges. For most types, we can choose at which pin of the microcontroller the created signal would be accessible, or when the internal counter reaches the threshold, a rising or falling edge should happen on the output. Sometimes, a PWM module allows the control of several PWM outputs, which may have different duty cycles. It is usually possible to adjust the timing of these outputs relative to each other, that is, to turn them on or off simultaneously, or to operate in opposite directions. It is common for microcontrollers to have multiple independent PWM peripherals that can be synchronized, allowing their counters to count simultaneously. A further useful feature of PWM peripherals is that their operation can be modified by other output signals. For example, an external error signal can block the operation of the PWM outputs, protecting the circuits outside the microcontroller from damage.
Yes, it has several features, but don't be scared. Each microcontroller's datasheet contains a detailed description of the PWM peripheral and its functions, so you don't need to know them by heart.
That's right, I listed them only to hear about it once. So you might remember later if you need one of the features, and the details are in the datasheet. Let's have a look at some examples of what kind of tasks we can implement with a microcontroller PWM unit. Probably the simplest application is when we don't change the duty cycle of the signal, but we alter the frequency. This can be useful if you would like to produce a sound with varying tones. Another typical mode is to generate a fixed frequency PWM signal with the duty cycle set in the program. We can use this to continuously regulate motors or the brightness of an LED, and after filtering, we can create an analog voltage too. Perhaps the most complex mode of operation is to generate a PWM signal with a duty cycle that varies from cycle to cycle. This can be achieved by executing some instructions at the beginning of each PWM period, which calculates the required duty cycle and sets the appropriate registers in the PWM peripheral. To do this, we need to use interrupts, which, as I said, will be discussed in a later video. This mode can be used to achieve fast regulation. It's mostly used to control motors and switching power supplies. Of course, the PWM unit can be used in several different ways as well, and this depends only on the programmer's imagination.
Yes, this was only a very brief part of what PWM can be used for. But now we've come to the end of the video. Next, we will learn about the PWM peripherals in our 8 mega microcontroller. See you there.
Bye!
Bye.